Okay, welcome. I'm happy to be here in Bochum again. Last year I also had a presentation, but that was online and I really didn't like it. And but it was also about C++ OS, but that was really mainly theory and not really something that works. And I thought for this year I will change that. So I bought some hardware, and I hope it will actually work. And all this is about for the Raspberry Pi Pico. That has a chip with a dual core, and it's a very special dual core. And so I thought, well, I look what I can do with that one. And yeah, the first is what is actually C++ OS about. And the idea is that C++ by now has quite a lot of interfaces that actually provide the functionality of an operating system. And of course, below that, you need some operating system. But you don't need really the native operating system interface if that interface is in C, but you can use the C++ interface. And so the idea of C++ OS is simply provide this C++ interface natively. That's the idea of C++ OS. And well, if you go for the chip on the Pico, it has dual core, but it's pretty hard to synchronize that, or at least special, not very hard, but special. And yeah, I just was interested what I need to do to get it working. And why would you want to use it? Well, the idea of not using some native real-time operating system is whenever you change it, you have to change everything. And also, if you use a specific one and then you change jobs and use another one, you have to relearn everything, especially all the bugs that the system has. And the workarounds you have used and things like that. And if you have a C++ interface, well, that is standardized. You have always the same. And yeah, well, why did I use this? Well, actually, Odin brought me to this because on last year at the conference, he just said, well, he now uses this chip because it has a lot of RAM, but he didn't touch the second core yet. And so I decided, well, okay, let's look at that chip and see what I can do with the second core. And so that is what all this is about. The next few slides are from last year, so I will go through them very quickly. So C++ really has a lot of interface for operating system, including a lot for synchronization, which is important here. And but it also has other things like time, and you have a standard sleep. There are no timers, and one of the reasons for that is we don't really have an event system yet. There are, well, not really a lot of support in the standard yet for events. There is an event model in networking TS, but that will not be standardized. And yeah. So we will have a new one. I will come to that in a second. And we have coroutines. We don't really have real library support for coroutines yet. We have it for generators, but not for tasks or things like that. And we have file system, and we have a lot of other things. Like, for example, I actually like SED string. I don't have any malloc. So I cannot use the normal SED string, but I can use the SED string from PMR, where I provide my own pool, and that is fine. And that is all available with C++. And so here's an example that I actually originally ran on the AVR at 8-bit. And I had to contact, I had to file a bug report for GCC, and Jonathan Wakely actually fixed that within 2 days or something like that. And then it worked. So I actually use a vector of strings. So here I have a vector of string. I don't have malloc, so I just provide my own buffer. So here I have my buffer, and so this, and then I have this memory resource, typically a monotonic memory resource, and that just provides all the memory that's required. And then I can just use normal C++ programming. And I said before, we don't really have an event system in C++, and there's a proposal called STIT execution, or P2300, and that tries to provide an event system. However, that is a very special event system for a very special use case. And unfortunately, for me, that is a very limited use case that often doesn't work. It works very well on servers with high-speed computing and this kind of thing, but it doesn't really work well for embedded systems where you often want to have some buffers between two stages and things like that. So I try to change that, but yeah, we will see what comes out of that. But the general idea behind that is not really that bad, because it actually puts things together in an event chain. So you have something that provides the first event, which is the sender. Then you have some receiver that gets that event and then creates the next event, and so on, and you can chain all that. So the interface itself is not really bad. They just have one specific thing in the specification that makes it unusable whenever you want to have buffers between those stages. And another thing that STIT execution provides is so-called execution context, because you not only have a normal Linux, for example, with threads, you also have, for example, something like limited thread pools, or you have some executor that runs on a GPU, or you have something that does everything cooperatively, so you don't have preemption. And all this is currently not in C++ in the standard. People do that with C++, but it's not in the standard. So P2300 actually provides a framework for that. It doesn't actually provide any concrete executors, not even a thread pool. But it says what an execution context is and what it has to provide. It doesn't provide an API for that, but it says that it has to provide schedulers, and for the schedulers, there is an API. And yeah, I already talked about the event interface. And another thing, and that is actually something I'm working on, is queues. We have a queue proposal for a very, very long time. I think the first version of that proposal was presented in 2012. We still haven't it standardized. I hope to change that, but yeah, sometimes standardization is a very difficult process. But I think it's a very important communication mechanism, especially if you have an event system where you have some buffer between those events. And yeah, for example, if you have a queue between an interrupt service routine and normal tasks, at least one side needs to be lock-free, or you at least need a lock-free interface. And sender-receiver doesn't really work with queues. And that's the problem with the specification right now. And as I already said, I hope to change that. And that is what currently is the state for C++. So what does C++ OS provide? It wants to provide everything, but of course currently it provides only a very tiny part of it. And I originally started on a Cortex M4. So even at that time, I thought about, well, Cortex M4, that actually could be dual core. So I thought about SMP, symmetrical multiprocessing. And I decided upfront, no, I will not do that. So in my system, you can never migrate a task from one core to another. My underlying implementation simply doesn't support that. But otherwise, well, I did that port for the Cortex M4, actually only Cortex M3. I didn't provide the floating point part. And I did a port for the AVR, Arduino and things like that. And it works pretty well. It's just pretty slow, because the AVR with 16 megahertz is not pretty fast. I also started non-native implementation based on FreeRTOS for the Espressif, but I decided not to continue on that because there is a mismatch between FreeRTOS and what I want to provide, and doing a lot of workarounds wouldn't make a lot of sense. And actually, that is why I was pretty happy with the Pico, especially the Pico W, because now I have essentially the same hardware I had before with something that I can actually use and support with C++ OS. Yeah, and I actually libstd C++ can be built for all the embedded targets. It just gives you sometimes on linking that something is missing. So if you want to allocate memory, it will complain, okay, it doesn't have S-break and all these kind of things. And so you have to provide it, and C++ OS simply tries to provide these things. And so I already said the RP2040, it's based on ARM Cortex M0 Plus. And the M0 Plus is really not designed for multi-core, but they decided to have 2 cores of them. And so they actually provide special synchronization hardware that you can use. And so there's a CPU ID, you have spin locks that you can use to synchronize, and you have a FIFO where you can send messages from one core to the other. And, well, SMP sometimes is called shared memory processing. Well, of course, we have shared memory processing because we only have one memory. And we actually don't really have a cache. So, yeah, I said the processor doesn't have cache coherence. Well, you don't have a cache, so you don't really need cache coherence. But the point is, if you have read, modify, write operation on something, you need to synchronize that with the other core. If you just do a load or a store, that is fine. You don't have to synchronize that. But as soon as you want to do more, you have to use the special synchronization mechanisms. And I started just using the Pico, and initially only a single core. I just wanted to make sure that everything works. I already had a port for M0, so it more or less worked out of the box. I just had to adjust all the peripherals. But pretty soon I noticed that I cannot really use the Pico SDK because they do some resource management that really clashes with what C++ OS does. And that made things a little bit more complicated. So I created my own header file from the SVD. And in my normal programs, don't use any part of the SDK. For some things, I use it, and I make sure that I don't use any things that are problematic. And I create a static library from that and just link that static library to that. So I never have a clash between the Pico headers and my own headers. And for the single core, I have all the support I had before for stat mutix, for example, condition variables, and stat atomic, because underlying all the other synchronization, you always need some atomics. Atomic wasn't complete. I think by now it might actually be complete. The last one I added was the exchange function. And yeah, just a simple example. So it's this one. I have 3 tasks. I have my execution context, which just provides a preemptive multitasking scheduler. And I have a task that blinks an LED. I have a task that prints some values. And then I have some tasks that simply count to keep the CPU busy, just to see how that works with my schedulers. So this is a pretty nice program to test my scheduler. It doesn't do anything useful. And however, I can try to flash that. Oops. I probably need to switch it on. Yeah. And something doesn't work because, as you can see, it's not flashing. It's this one. This is a Pico probe. This is just for JTAG. And this is the one I actually use. And it's not flashing for whatever reason. Sometimes reset via JTAG doesn't work very well. Yeah, now it works. So that's fine, and every 10 seconds there should be some output here, which gives you the count of the 3 busy tasks. And I actually use atomics. So let's see, here the busy tasks. So I actually use some atomics to make sure that they are really properly accessed, so I don't have any undefined behavior. So that's all about single tasking, and that is essentially what works a year ago. At that time, not with the Pico, but with the other hardware. So that's not really new. Now, before I actually come to the Pico, well, when I thought about the dual core, I thought, well, what do I want to provide as executors? And in a lot of cases, if you have a dual core, well, you might have several tasks that run on one core, but often you dedicate the second core to just a single task. So I actually decided to provide more than a single executor. So yeah, I already talked about P2300, and but I provide that thing that you have seen is the exec context. That is just a normal, classic, preemptive multitasking scheduler, which does task switching, and I think I do it on a millisecond base, but you can actually change that if you want. And I decided also to provide a single context where you simply have only one task. And you don't have any idle tasks. So whenever you block, well, you either do a wait for interrupt or you do a busy loop and waiting for something to happen. But there's nothing else you do when your task doesn't have to do anything. Well, you just wait. You don't have anything else. And that is the reason why it's actually based on real hardware. It's different than a loop executor that I also have. That loop executor, that is meant for if you want to have an executor where you can do something like cooperative multitasking or something like that inside of a task that is running on an exec context, for example, or if you are on a hosted machine in a thread. So there you can have a loop executor. The single context is different because that is really on the hardware. And then I also have an interrupt context where I simply can put the interrupt service routine I started on the interrupt context, and that is a template, and the interrupt number is the template parameter, and it will start that interrupt service routine as an interrupt, but I have only implemented that for the AVR, not for the RP2040 yet. And well, now if I have different kinds of executors, I have to think about how do I synchronize between those executors. And because all the classic synchronization mechanisms, except atomics, are really only specified for the thread. Atomics, they work everything. Well, basic atomics. If you go for atomic notify or atomic wait, of course, that atomic wait needs to block, and that needs to be on some execution context, and well, that is only specified for the thread. And if you want to do your own, well, you have to think about it. And well, there's a very, very old proposal. You can see that on the low number, 73. It must have been about around 2015 or something like that, where Torvald Riegel actually proposed an event. And at that time, it was to bridge the gap between normal threads and coroutines. And but it never went anywhere. So that is essentially that. But at that time, I looked at it and I kind of liked it. And I actually used something like that event as the basic implementation mechanism below my mutex or condition variable. So I actually already had that, but again, only for, well, my threads. So I decided, well, okay, I can use this event if I know about the execution context, I have to do different things for notify and for blocking. But if the event knows about these things, then I can still base everything on the event, and then that can handle synchronization between all kinds of different execution contexts. And but I don't want to write an event for each different pair. So I don't want to do an M-to-N thing. And well, it actually kind of worked out that I can do that really on a single-ended base. So I have to do the notify mechanism for each different executor type, and I have to do the block mechanism for each different executor type. But I don't have to do all the combinations, which would be really a problem, because for a mutex, where you can have 10 different tasks waiting on a mutex, and they could be on 10 different execution contexts. And that would be really a problem if you have to do all the combinations. So this essentially kind of works, and so I provided those events. I already had them, and I added now a new one, notify one, and that actually is templated on the executor, so I need an implementation for each executor type that I support here. And based on that, I can actually implement queues. I have a classic queue that is actually based on mutex and condition variable. As you can see it in the books. And I now have an event-based queue that actually you can use to communicate between different execution contexts. Right now, this is really only single-ended. I need to think a little bit about it to make it multi-ended. So you can only have one task for the pushing side and one task for the pulling side. And I separated the implementation. I think I have it somewhere. I have the body, and then I have one pull end and one push end. And so I have a small test for that. This is still single core. So I actually have two queues. I have one queue. Well, I have two queues, and for both I have a push end and a pull end. So the first task simply creates some numbers and pushes them into the first queue. That lint is my login, so this is just debugging. And then all this is really full of debugging code still. Then I sleep for half a second, and I push 100 numbers in there, and then I just go into an endless loop, because the task should never end. On the second task, I first sleep for 10 seconds. And my queue has only 16 entries, so the first queue will actually have to block, because the queue is full, until the second task starts to read the value. And then the second task just reads the value from one queue and pushes them into the next queue. And the last task, that just pulls from the second queue right away. So that starts with an empty queue. So I actually have tests for the full condition and for the empty condition. And then again, I just have again my execution context, and I start all my tasks, and I have my print task, and that is again mainly for debugging. And now I have a problem here. So this is still the previous one that is now running for 710 seconds. Let's flash it. So I have them here, but unfortunately I don't have this one. I have to kill it. And now I can start it again. Ouch. Yeah, that's a problem. Well, thanks. Okay, so yeah, but unfortunately, for some reason, it didn't reconnect my USB. Well, let's just disconnect. And reconnect. This work? Now it works. Okay. So, and now just starting it again. Yeah. So, yeah, now you can, okay. Yeah. So it looks like all my Q tasks go to the second one, and the first one is really only the print, but that's okay. But I need the other UART for the next demo, so that was the reason why I really wanted to get it working. So now let's talk about the Pico, and especially the Pico W, which has a Wi-Fi modem. And so the idea was, well, I could actually do a Wi-Fi speaker. And I already had one previously based on the Espressif and FreeRTOS, but I didn't really like that, so I decided to do that using the Pico W. And so it doesn't, the Wi-Fi modem is special because it uses SPI, but it cannot use a native SPI, so it uses a PIO for that one, and I2S is exactly the same. There's a PIO driver for that, and I just use that one. And so the idea of the Wi-Fi speaker is just, well, there's a Snapcast, and they encode the sound via Opus, and so decoding that might take a lot of work, so I decided to do that on the second core. I do all the IP stuff and this kind of thing on the first core, and the decoding on the second core. Unfortunately, I couldn't get the Wi-Fi driver working because I couldn't use the SDK, and the other turned out, well, I put a week into that and it didn't work. So for the demo here, I decided, okay, I will just go for the UART connection, and that was the reason why I really wanted to get the UART working. And I just modified my Snap server to write to a serial port. And so the idea is the interrupt service routine for the UART pushes the frames that come in into the first queue. The decoder waits on the first queue, decodes them, pushes them into the second queue, and the interrupt service routine for the second for the I2S that just reads from the second queue and pushes them to the I2S. And yeah, but for that I needed to get the dual core working, and currently on the second core I only use a single context, and the blocking should be using by wait for interrupt. For some reason it didn't work, so I just do a no-op and a busy wait. And the atomics are based on spin locks, and event notification is based on a FIFO. So whenever an event becomes unblocked, I check, is it on the other core, and if it is, then I send it through the FIFO. And I have the queues there, and but I also have my wireless speaker. So here it is again. That is actually from the previous version, including this one. That was my original hardware based on the Espressif. And but now I have here it is. So the point is, on the first core, I don't have any task running because everything is done in the interrupt service routines. But I still have my print tasks. So I have at least one task on it. And here, and maybe I should go down here. Here are my definitions. The first core is my normal standard exec context, and the second core is a single context. The one is the core number. So I start that on the second one, and then I just start my two execution context. I start my print on the first execution context, and I start the decode on the second execution context. Well, and maybe so here's my decode task, and the interesting part here is, here I create my queue ends specific for my executor. So I read from the, so I have the correct implementation for the queue end for this specific executor. Let's flash it. Here's my snap server. Oops. Okay. So for some reason, my M player is still running. It's unfortunately very low. So oh. It looks like it was pushed in a queue and it is still there. And unfortunately, I cannot change that. It goes for about 10 minutes. So I cannot change the volume because I can that only on the software side. But yeah, I hope you can hear at least a little bit. Okay. So it actually works because it's so low volume, I can actually keep it running. And, well, I also wanted to do the coroutines. Well, first, I didn't have time for the coroutines. And second, here, I really don't need coroutines because without the networking and without any additional thing like volume control, for example, or things like that, I cannot use coroutines here. But what you would have to do is that for the queues, well, I will probably switch it off anyway. For the queues, you need coroutines for push and pop. And then you need something behind that, behind the scene, where you can actually get those events and wait on those events. And so you need some select or epoll mechanism. I actually already have some implementation, but I only wrote it down when I was on a train, so I could never really test it. So it will probably not work right now, but at least I have ideas how to do it. And yeah, I will skip the sender receiver because that doesn't work very well. And yeah, you shouldn't use it because it's still just a toy for me to test everything and to try things out. And finally, if you actually want to look into the code, I have it on GitLab. I haven't pushed it to my normal C++ OS repo yet because it has a lot of debugging stuff and also quite a number of bugs are still there. But all the code that I have downloaded here, you can find it there. So that's it. Thank you.